We are little ahead of time, but we can start because our next presenter is ready. So our next presentation topic is exploiting fiber control for delayed failure in 3D printed fiber reinforced polymer composites. And I'm happy to introduce our next speaker, um, Dr. Shreya Vemuganti. Dr. Shreya Vemuganti is an assistant professor in civil engineering at the University of Oklahoma with a PhD from the University of New Mexico. Her research focuses on 3D printed fiber reinforced polymer composites for infrastructure, including polymer matrix, nanosynthesis, bridge deck overlays, and strengthening methods for concrete elements. She has secured over $1.4 million in funding from agencies like ODOT, NSF, and USDOT. Dr. Vemuganti is an active member of ACI 548 and has been involved in multiple international polymer concrete congresses. In 2022, she won the Ralph Pove Jr. Faculty Award. So let's welcome our speaker today and listen to her presentation. Welcome, Shreya.
Hello, everybody. Good morning or good afternoon, wherever you are. Thank you for being here. Today's presentation really is a lot of my PhD work that I would like to present with and share with all of you because it is a very important and current relevant topic. So firstly, I'm from the University of Oklahoma. We're the structural engineering faculty here. We're six faculty, very dynamic, going from nonlinear modeling to risk analysis to climate change modeling, and of course, my area of expertise, which is materials and particularly fiber reinforced polymer composites and also additive manufacturing. That's my team down there. So everything that we've been doing here is really because of them. The work I'm presenting is part of these 8 publications, so you're more than welcome to go dive deeper into anything that I refer to here, which you're interested in. A lot of the work, of course, was conducted in the University of New Mexico, the Dana C. Woods Materials and Structures Lab, where I received my PhD from, and then my students took over some of the work, and we published more in terms of concrete as well, which I'll be briefly going over today based on the time. So before we get into 3D printed fiber reinforced polymer composites and fiber control and all that, primarily talking about FRP itself, right? We have two primary components, which is fiber and the matrix. Together, they become a composite material that not only provides stiffness and strength because of the fiber contribution, but also protect and transfer the load between the fibers due to the matrix component. So the entire composite itself, it's superior than its individual attributes. And both the fiber and the matrix play a crucial role in the composite material. Of course, fiber reinforced polymer composites are more popular than ever in different kinds of fields, as well as different properties that they demonstrate. You name it, they have it. Long-term durability, lightweight, high strength, impact resistance, corrosion resistance, which is one of the primary uses in terms of civil engineering aspects. So rebars with carbon and glass fiber reinforcement demonstrate great corrosion resistance that other materials in civil engineering cannot demonstrate. So in terms of strength, if you look at FRP itself, it's stronger than steel. If you look at typical CFRP, GFRP numbers here, the lack of ductility is what is something which is a growing topic, but also something that hinders its growth in infrastructure applications. FRP is not a fail-safe material. It demonstrates a brittle elastic stress strain behavior, as you can see here. I can turn on a laser pointer. So if you see this linear elastic stress strain behavior compared to steel, which demonstrates this nice ductile behavior, failure strains above 5%, that helps avoid brittle and abrupt structural failures. So the brittle nature of FRP is something that has been looked at since several decades, but not necessarily has achieved a tangible solution that could be, potentially solve this issue of ductility. Of course, we have conservative design limits, so to take full advantage of its tensile strength, its ductility definitely needs improvement. So, multiple efforts were made in the past, especially something called fiber hybrid composites. Um, if you look at these composites, they either demonstrate interlayer or intralayer or intra-yarn kind of a structure. And when we say interlayer, these are basically layers with different types of fibers that are stacked on top of each other. When we look into an intra-layer structure, two fiber types are mixed within the layers and they are woven into a fabric. And in the intra yarn configuration, the fibers are basically commingled, but it's at the fiber level itself. So, if we look at the different behaviors that these can demonstrate, we have a linear behavior that typical FRP composites has discussed demonstrate. We have pseudoductility, which is a flat topped stress strain curve of a, monolithic tensile test setup, and a ductile behavior more so that it offers that strength needed but also prolongs its failure to a more higher strain. But the limitations of these fiber hybrid composites were found to be that there are high strains possible, but only at low strengths. There is therefore a large reduction in capacity, though they can offer those high strains, something like this. The second limitation that was primarily pointed out is misalignment of fiber types. There is not necessarily a controlled way to align these fibers, and therefore those misalignments can cause deviation in mechanical enhancements. So even though enhancements are seen, there can be very high deviations because there's not a controlled way. Of course, intermingling and intermixing these fibers is not at all a easy task. It's highly challenging and cumbersome in terms of fabrication. And this in turn results in manufacturing defects, quality control, and again goes back to that mechanical deviations that are seen. One other type of failure that is noted but not very much observed is what we call a progressive failure. This is when we have configurations that can lead to high strengths, but there are abrupt failures. However, the remaining composite itself can carry on the residual load and therefore that high increase. And again, there is an abrupt failure. So, progressive failures are not uh, targeted, but can be a consequence of some of these fiber hybrid composites, eventually leading to a pseudoductility or a ductile behavior. So, for this particular topic that I'm presenting here, the goal really was to achieve a ductile or a pseudoductile FRP composite. But the goal to achieve that is using only one type of fiber, meaning is it either glass or carbon, doesn't matter, but it's only one type of fiber, which is in other words a monotype fiber instead of a hybrid type fiber. And the way we want to achieve that goal is with 3D printing. So I'm going to discuss some of those outcomes of this particular process that we adopted. So, how monotype fiber? The entire hypothesis started from a patent that has been listed in one of the eight publications shown before. So, this entire hypothesis revolves around engineering basic mechanics of the composite, the fundamental mechanics of engineering the shared stiffness between different layers. So FRP composite consisting of different layers or a stacking sequence that has different orientations, fiber layer thicknesses, how the shared stiffness between these layers works out. So these were governed by load sharing ratios, and they have been determined using one, which is the modulus of elasticity, two, which is the area which layer has been occupying, which is basically if you look at the layer 1 can occupy n1 times a thickness of, let's say, 0.1 millimeter, and this can be a particular fiber orientation of, let's say, theta 1. So that will be number of layers times the layer thickness will get us the area that this layer has been occupying. And you have I, which is the layer number itself. So these parameters govern what kind of shared stiffness that the layers can really demonstrate. If one layer takes the load and at its own strength fails, how do the rest of the layers really pick up this residual load and kind of demonstrate, that progressive or a delayed kind of failure mechanism? So to get into the methodology itself, the process itself, we've used nylon-based thermoplastic filaments, and the fiber itself is a fiberglass filament. And the mechanism that we've used in the 3D printing technology is a continuous fiber extrusion, meaning this doesn't relate to chopped fiber. It is a mixture of the thermoplastic along with the chopped fiber that has been input into a filament maker, which makes a filament that has both now a fiberglass component and a thermoplastic component. So this in itself is a fiber reinforced polymer. And then we basically use a continuous filament fabrication, which in other words is a way to print or extrude a thermoplastic filament along with a continuous fiber in the same layer. So in the exactly same layer made with a thermoplastic filament, you are also able to input a continuous fiber into that exactly same layer. So if you can see this demonstration here, the same layer has both a thermoplastic component and the white color fiber component. What this technology does is, because of its potential to actually extrude continuous fiber on the layer, you are able to control with a G code of which orientation this continuous fiber can take. Because chopped fiber, if you look at it, you are not able to control the direction of the fiber or orientation of the fiber. But continuous fibers, you are able to coordinate and govern in a way such that the print head itself gets the input from the G code, where what orientation of print needs to be achieved is inputted into the software. Now, how accurate that is, we have also looked into that, but a quick look into the 3D printer components itself. We have the print bed here and the fiberglass filament spool here. We have a thermoplastic filament spool that's behind the printer, which is not visible in these pictures. The print chamber itself is not a very highly controlled print chamber. It has a small opening, but the temperature still doesn't reduce very abruptly. Then you have a print head system with two nozzles, which is a fiber nozzle as well as a thermoplastic nozzle. The loading tube itself gets into the print head, carrying both the thermoplastic filament and the fiberglass filament, which respectively come out of the specific nozzles. These nozzles heat more than 223 C in order to accommodate both the thermoplastic and the fiberglass. For the fiberglass, it's more, which is about 270 C. So, as I was talking about accuracy, how do we determine whether the orientation that we require is actually getting on there onto the bed, right? How do we know whether the orientation that we ask the G code to extrude onto the print bed, how do we know the accuracy of it? So we've done some microscopic investigations to see how the fiber is actually aligned with the thermoplastic. If you look at the picture B here, which is B here, the 0 degrees angle is very accurate. We can achieve 100% accuracy in this regard. When you go to the next fiber angle, which is like 12 degrees, we've still been able to achieve about 12.13 degree of extruded final product, which is still very, very accurate. 24 and 30 degrees also have only a 0.12 and a 0.17 degree variation in them. So this shows how accurate 3D printing can be in order to get the final product which you have designed to contain certain orientations or thicknesses or things like that. This is just an example. So if you look at the project itself that I was talking about, we started off by just printing these orientations like 0 degrees or 12 degrees or 24 degrees because we wanted to achieve their properties. Properties being both the elastic modulus, the tensile strength of the material, as well as the tangential modulus in order to input it into the finite element model. So this is a standard ASTM D3039 test that we performed. By testing all these composites, we were able to achieve a data set of how each of these fiber orientation and the composites with that particular theta behave. So if we look at the failure modes of these composites, 0 degrees fails pretty good when compared to a traditionally manually fabricated fiber reinforced polymer composite. So that typical broom-like failure has been noted. So you can definitely say that 3D printed composite fails in the similar way to a manually fabricated composites. The other angles, which are very cumbersome in achieving in a manually fabricated setup, we were able to achieve it in a 3D printed setup. So you're able to get the fiber orientations and the properties that they demonstrate. So if we look at that load sharing ratio, we came up with a design in order to have the least variation between layers. So this was our most preliminary design, and you will see that as the work progressed, we've been able to achieve very, very good designs in terms of the variation of the shed stiffness. So if you had a 12 degrees, 24 degrees, 30 and 45 with so many number of layers, we were able to achieve about a 30% variation between the shed stiffness. So that gave us that gave us a design of basically the stacking sequence and the print direction that we were able to embed into the 3D printer. So determining how many angles and how many number of layers for each angle, all that helps in coming up with the stacking sequence, which is basically directed by these calculations. So overall, when we started 3D printing this preliminary design, the first layer would be a thermoplastic floor, followed by the angles that are larger, and in a symmetric way. So if you had minus 45, that would balance out with a plus 45. And after the highest angle would be the lowest angle, and then and therefore the middlemost angle being the least amount, the smallest angle possible, and then these layers mirror them. So everything else on top is also symmetric. So if you see the total number of layers here, we have about 14 plus 4 plus 4 plus 1, so about 23 layers in total that have been 3D printed. So if we look at this particular preliminary design, we did achieve somewhat of a progressive plus ductile. If you remember, I showed you how ductile, progressive, pseudo-ductile, linear work. So we see a nice linear behavior in the beginning until the tensile strength of the composite has been achieved. Then we saw a really abrupt failure, which is indicated as drop 1 here. If you see, all the 5 composites we tested demonstrate similar kind of behavior. After the drop 1, the higher angle layers, such as the 45 degrees, observed some debonding from the remaining composite. So this is corresponding to drop 1. Then we have drop 2 here, which was followed by a small drop. Though abrupt, it was smaller in capacity. And then we had drop 3, which the result was basically the entire damage resulting to failure of the coupon itself. So in particular, if you see the strength and strains of the discrete fiber orientations, so the orientations that just had the 0, 12, 24 and all that, when combined this way, definitely the behavior is different. The strengths for 0 degrees are somewhere around 600 MPa. However, for 12 degrees, they are lower. When you have combined it in a composite, they're even lower. So definitely there are differences between the single fiber and a combined kind of composite. So the important thing was to understand how does this composite behave in a perfect situation or a perfect bond situation. How would this composite really behave? For that, we performed some finite element analysis. We used ANSYS modeling, and we assumed a perfect bond between layers, which in all reality is not possible. So once you get that perfect bond between layers, the same exact design behaved somewhat differently than the original. You can clearly see there was no longer an abrupt failure. There was no longer a large drop in capacity. There were more smaller drops in capacity, which is more of that progressive kind of failure that we've seen in the past. So a considerable loss in load capacity of the composite, if you see in the experimental, it's because of an early stage of damage due to multiple layers failing together. So because of those multiple layers failing together due to the bond that is between those layers, you see that because of a perfect bond, that is not the case that is happening here. And there was interlaminar effects in the load transfer between layers, and they could be controlled if the load transfer between those layers is controlled. And that we hypothesized based on mechanics and different kinds of bond related studies, that because of that early stage damage where multiple layers are failing together, we should really look into how these layers are connected. So if they are connected with a weaker kind of interface, how does the load transfer work? Theoretically speaking, it must be dampened as well, because matrix is where the shear transfer happens, so that one fiber, the load that one fiber takes is transferred to the other fiber to take that residual load. If that shear transfer itself is weakened, then that load transfer doesn't happen, and therefore one fiber breakage may not affect the other fiber's damage. But the problem here, though, is that shear transfer, if dampened, also affects its mechanical properties, which is strength and other kind of properties. So considering this, if you see a brittle uncontrolled failure mechanism in a strong interface, whereas an interfacial cracking or a debonding in a weak interface, an alternative kind of bond needs to be established. And we are talking about 3D printing here, which is mostly like a continuous process. So how do we establish this alternative bond between the layers? What we went ahead and did is we kind of established three configurations, which is we considered fully bonded configuration, which is the process of 3D printing just taking over and just continuously printing. Though it is not a perfect bond, we are considering that as a fully bonded configuration. The second configuration we established was what is called a thermal block configuration. I will explain in with pictures what that means. And the third configuration we established is a fully debonded configuration, meaning the fiber orientations are kind of separated without any kind of bond between them, and see what that leads to. So if we take a fully bonded configuration, because all of those are combined, the fully debonded configuration is quite the contrary, which is basically, if you look at these angles here, the legend of which is provided here, you have color-coded angles that are completely separated from one another. You don't have any kind of bond between them to actually allow that shear transfer. If you consider a thermal block configuration, what we did is, since cooling and heating environments really affect polymerization and the ability of layer welding, which is basically welding the layer that has been deposited with the layer that will be deposited. So layer N, which has been deposited, needs to weld with the layer N plus 1, which would be deposited. And for that, temperature requirements, the print chamber conditions, all that is a must. What we did is, in order to create that alternative bond between these two layers, we affected that interface that there is between layer N and layer N plus 1. What we did from experiments, what we noticed is that when we immediately print layer N, the temperature on that layer N is about 40 degrees. After we've waited 20 minutes, it's about 29.6 degrees. After we've waited about 40 minutes, it reduces another 20 to another 28.2 degrees. So forth until 90 minutes of a print lapse time, it's about 27.7 degrees at the layer interface. So to print the next layer N plus 1, instead of having some nice heated conditions on that interface, they actually have now a cold kind of a joint, which kind of affects the polymerization at that layer. Of course, waiting 90 minutes to do each layer is just an impossible and unrealistic task. So what we did is we used what is called dry ice. That dry ice, instead of taking 90 minutes to come down, that rapid cooling mechanism in just 15 minutes brought the temperatures to very close to 0 degrees. So we were able to achieve faster and much lower temperatures in order to create that debonding interface between layers. If you look at the paused layer itself, you see that there is a nice separation between layer N and layer N plus 1, which is demonstrated using this microscopic picture here. So the technology being hopefully in the future, if there is a possibility to incorporate this cooling mechanism in the 3D printing technology itself, that will save a lot of time and effort. But for now, to demonstrate how this alternative bond can be achieved, we adopted this kind of a procedure. So for the first design, which is a combination of 12, 24 and 30 degrees, what we saw is, in a bonded configuration, there was a really abrupt kind of drop. The strengths achieved were higher than what we saw before, but of course not as much as 500 or 400 MPa that we've seen for individual fiber orientations. If you look at a fully debonded, that was fantastic because it showed a nice progressive failure where there was a small drop. However, we were able to achieve that increase in capacity due to the other fibers just not being damaged. So, because of one abrupt failure, the other fibers did not get any effect because of that lack of bond. The thermal block, which is more in terms of the 3D printing process itself, we've seen a nice progressive failure. Though the load did not increase after the first drop, we still saw that the other layers were maintaining that load for a certain amount of strain percentage. So if we saw in this first design, a fully debonded configuration got us to up to 5% strains, although at a compromised loads, but we still have a better configuration compared to the bonded, the fully bonded type. Oh, so in this case, if you look at the bonded, one drop, brittle failure, completely broken composite. In the blue color, which is this box here, drops 1 through 5, we noticed sequential kind of failure or damage in the layers, resulting to failure of the entire composite. And then in this black box here, you've seen some drops that were able to completely fail the composite, but in a sequential manner. In design 2 and 3 also we've seen similar kinds of behaviors. Fully debonded configuration in fully bonded configuration in design 2, which is the red line here, attributed to the red box here, which is failure in 2 stages to 3 stages. Blue box fully debonded, many drops were seen, but also many kinds of damage in different layers, not all together at once. Drop 7 finally showed that complete damage. If you see the black color line here, again a progressive stepwise sequential failure, thermal block, at a compromised load compared to the bonded, but definitely higher than the fully debonded because there is still some kind of bond to allow the shear transfer and therefore the strength increase, but there is not enough bond as the bonded to get that strength. However, the bonded had abrupt large drops, whereas the thermal block had smaller kind of drops or load capacity drops. And the design 3, if you look at it, the fully debonded performed very well, and the presence of the 0 degrees also had helped very much because there was some kind of brooming at the top. If you see this first image here, after that brooming happened, there is still increase in load capacity, and then there was a reduction in capacities with respect to the drops. But the highest strain was achieved for this fully debonded configuration. So takeaway from these 3 stress strain behaviors of these 3 different bond configurations were definitely there is strength compromise because of the lack of bond. However, what you see as a progressive and almost ductile that we presented before different configurations, that is lacking in the fully bonded configuration. So if there is in a way future technological improvements where we are able to achieve this bond in the 3D printing itself, that would be a great benefit because that way we can also maintain the integrity of the material itself. We performed some ductility index measurements using the typical energy-based approaches by Grace. And designs 1, 2, and 3 performed very well in terms of fully debonded configurations for ductility. Bonded configurations obviously lack that sense of ductility, but the thermal block configuration of design 1 showed huge improvement on the bonded one. Again, strength, modulus, and strain at failures, you will see that the bonded will be at the highest strength in terms of design 1 and design 2. But the design 3, you have a fully debonded one in terms of strain, that is higher strain at failures for fully debonded. And that control bond or a thermal block also is higher compared to the bonded, which we were trying to achieve. If you look at just comparisons between traditional, unidirectional, typical GFRP composite, it's about negative 89% ductility when compared to a 3D printed GFRP. A grade B steel, of course, is the most ductile compared to this graph here. It's definitely higher ductility compared to 3D printed GFRP and typical GFRP. But compared to that typical GFRP, if you see 3D printed GFRP is doing pretty well on the ductility index side of things. We also quantified this particular bond using some interlaminar tests and interfacial adhesion tests. So if you see this particular test here, this is a shear strength, interlaminar shear strength test for the different kinds of bonds. In a completely debonded, we are not able to perform this test because the failure mode is slip. So in the bonded configuration for this interlaminar shear strength, a control bond is 25% reduction in the bond strength itself. So of course the bonded and the control bond differ in terms of bond strength, and this is a way to quantify it. These are ASTM standard tests. This one is a peel test, which is basically a T-flange or a dual cantilever beam that we put into a tensile testing machine, and we are pulling one of the flanges. So that has a 65% interfacial adhesion or interlayer adhesion strength reduction in the controlled bond, which is thermal block, versus the bonded configuration. So clearly from these two interlayer tests that we performed, we were able to distinguish between these two bonds, and because of that reduction, we know that there is transfer of load that is affected. Just looking at traditionally manufactured specimens, if you look at a Mateen bar, Owens Corning is the manufacturer of many FRP bars, rebars for civil engineering and construction uses. An OC Mateen bar is about 1000 MPa strength. Its process of manufacturing is very different. Achieving different fiber orientations is not possible, I would say, at this point in a OC Mateen bar or a pultrusion technique, which we use basically to produce these bars. It's a highly cumbersome kind of technology already, but to have to align those fiber orientations in order to get that resulting cross section is very challenging, and it won't be that controlled at this point. With the high mechanical deviations, we will basically go back to the same problems of fiber hybrid composites. If you look at a vacuum assisted hand layup technique, VHT coupon, that is produced using a manual technique of combining layers with with a matrix component and completely wetting out these fiber layers. That also is a very high strength coupon here. Getting different directions or adjusting and controlling directionality of fibers becomes again challenging in that process, because it is adjusting each layer to get that orientation. So control mechanical deviations are a problem there as well. If you look at a 3D printed coupon, it's about 600 MPa from the 1000 MPa of an OC Mateen bar and 900 MPa of a vacuum coupon. But the amount of flexibility and design variations that can be achieved in a 3D printed coupon is very high when compared to the other two. So that is one of the major advantages of using this 3D printing technology, especially for such goals where we want to be achieving some high ductility index composites. There is a lot of improvement potential in this technology. Right now, the fiberglass filament has about 50% fiber filament only. So the 50% is fiber and 50% is thermoplastic. Completely adjusting to that to even 75% or 70% of fiber will definitely achieve those strengths that we are not able to see right now. So if 3D printing technology goes in the direction of getting these numbers adjusted to have a more higher fiber volume fraction in the filament, we will definitely be seeing some improvements in these numbers as well as the designs that we just saw. So the strength will surely take a hit. We want to be able to put these composites eventually in concrete. To be able to do that, firstly, we need to understand how these composites even behave inside concrete. Does a traditionally manufactured FRP composite behave the same way as a 3D printed composite? There might be strength differences and strain differences, but that's not entirely what is important. How do they react with concrete? And why do we limit ourselves to only cementitious concrete? Polymer concrete is very, very highly popular, and we should be able to see if a traditional just 3D printed GFRP or this multi directional GFRP that we just presented and talked about, how does that react with cementitious or a polymer concrete? So one of my students here studied these composites in cementitious and polymeric cement mortars, and we observed that definitely there is good interaction between these composites, the 3D printed ones, with respect to both these types of concretes, especially in terms of cementitious versus polymeric concretes. We saw that cementitious concretes cannot necessarily get into small gaps. But if you take a fully debonded composite, which behaved the best in terms of strength and ductility, this polymeric concrete can actually seep into these gaps of about 94 micron even and allow that shear transfer to be so efficient that if you look at a ductility behavior, you have high strengths that are possible and a delayed failure strain in order to achieve some of the ductility kind of targets that there are with conservative standards. So if you look at just the behaviors of 3D printed GFRP in Portland cement concrete, you still see that their ability to withstand that strength is good in terms of just comparing it with a traditionally manufactured GFRP composite. So it's safe to say that we can use 3D printed FRP composites in concrete going into the future. We have some good directions that we can adopt in the future where we can possibly use some Bayesian optimization or some kind of machine learning techniques that inputted into a computational model can give us more in terms of the designs that are possible that can achieve this ductility or high ductility index. We can also look into further kind of materials aspect where improvement in the material or the material filament itself can improve the resulting ductility index and the strength values. Also, overall, I have some conclusions here that I can quickly go over. What you have just seen in this presentation is a pioneering work with FRP, and it's more importantly a design-based approach with different fiber orientations controlled with a mechanics and fundamental mechanics concepts. And the goal being developing those pseudo-ductile, primarily using one type of fiber only and not a combination of fibers. It's not to say that in the future we do not use multiple types of fibers. There is 3D printing technology where two different kinds of fiber elements can also be printed, and using that may also differ these results, but that design based approach that is following mechanical fundamental mechanics concepts should still exist. So we've seen some multiple designs with successful pseudoductility, and there's more progressive behavior achieved due to different kinds of bond configurations, and which is completely contrary to that uncontrolled failure mechanism that we saw in FRP composites earlier. Reduction in interfacial and interlaminar shear properties can be achieved and this reduction inherently dampens load transfer between layers, and that in turn affects how the failure mechanism is affected. Alternative bond configurations have been successfully modified using 3D printing technologies, and that has also been shown to successfully demonstrate some pseudo-ductility and behavior with high ductility indices. Debonding affects the strength and stiffness due to the modification in shear transfer. So that's what goes back to what we were saying as to there needs to be that optimal kind of debonding that still doesn't affect the shear transfer, but also gives us that progressive kind of delayed failure. But to think in the materials aspect also, that strength and stiffness can increase if the filament itself improves in terms of just the material. If you look at concretes, polymer concrete can impregnate in gaps ranging from 94 to 534 micron, which cementitious cannot impregnate, and therefore that could aid the shear transfer mechanism also in terms of the multiple fibers interacting with each other. There is, of course, a challenge of how many angles we can test experimentally, because it is a cumbersome process, right? So, in collaborating with kind of machine learning models or some kind of computational models that can make this continuous space into a solution space where we have some discrete fiber orientations that can be the properties of which can be obtained through computational models and then intelligently designed to make these pseudoductile composites. So some look into the future. Current 3D printing technology has limitation on thicknesses of the specimens and the fiberglass spool strength and stiffness itself. We talked about this. So therefore, to be able to produce higher strength and ductile designs, the 3D printing technology improvements in that would be a great future pathway. Further investigations by implementing some transient analysis interface elements in finite element models can also give us a lot of information on these particular designs and how else we can modify these bonds to be able to better achieve these ductile designs. For better shear transfer, but also through adequate bonding, a combination of bonded and debonded layers can also be a route that we can approach. This way, we might be able to achieve desired strengths and stiffnesses, but also that ductility that we are targeting. An alternative bond through some damping materials or hierarchical reinforcements at the interface layers can be introduced. We haven't researched that yet, but that's a great future pathway for all of you listening to think about this particular work. Testing of concrete beams, either cementitious or polymeric concrete with these new pseudoductile composites will give us some information of how they can benefit in civil infrastructure. So we have approached one of the designs, and we are hoping that we can take this work forward. Before I end, I do want to thank our funding agencies that are making all this work possible in right now that in University of Oklahoma that we are trying to pursue. I would also especially take this opportunity to thank Nex, because one of the projects that we are doing in terms of polymeric concrete is funded by them, and hopefully we can take this into 3D printing in the future. My advisor, who will be presenting next, I'm looking forward to his presentation. It's been a while, but he is fantastic in terms of polymeric concrete and 3D printing in that aspect. So I will stop here, and any questions I'm happy to answer.
Great. Thank you, Shreya, for the presentation. It was wonderful. It was a very good insight on polymer side of 3D printing, and as well as you included polymer concrete 3D printing, a bit of the study that your student did. So yeah, it was interesting presentation. Thank you so much. For the audience, please write your type your questions in the question box if you have any, and we will go forward with questions that we have already received. So, the first question we have is, so how do you look at using the polymer 3D printed composites in concrete 3D printing, marrying together?
That's a great question. So at this point, manual intervention of reinforcements into concrete is into 3D printed concrete is big. I know Sri Ramya has done some work. My advisor, Dr. Taha, has done some work. I am slowly getting into 3D printing concrete. We just received a great award and purchased an equipment, so we are slowly starting to build that. But our focus entirely is on that reinforcement incorporation. Either we are doing it manually, or with future technology, who knows, we'll be able to probably print together both elements of FRP composites and concrete. So the idea is right now manual intervention. That's the way to go about including these FRP composites in 3D printed concrete. Right now, there's a work that we're doing with the Southern Plains Transportation Center, where we are manually intervening these reinforcements, but our target is to do some durability studies. So we've exposed them to freeze thaw and chemical ingress and see whether that interface that the 3D printed concrete has, how does that um, uh, help in kind of degrading the element, because it is a open path for these chemicals to go in. So there's a lot of future potential there, and we don't have enough information, honestly. So it's a great aspect to look for in the future.
Yeah, if we are able to achieve this, it will be a fully automated system. So,
Yeah.
yeah. So moving forward with our next question. So the material you used in the beginning of your presentation for the resin and the fibers, are those ASTM complying? And or can you please explain what materials did you use in the form of resins and the fibers?
Sure. So, if I understood your question correctly, you're talking about the materials we used for 3D printing. Let me just quickly go to the slides. So if this is the material you're talking about, in this particular study, we used a nylon-based thermoplastic filament. We did not make these filaments. These are proprietary by a company called Mark Forged that allow usage in their own 3D printers. So actually, I don't know if you can see, we have a Mark Forged printer right here. Let me non-blur my camera. Yeah, so that's a Mark Forged 3D printer. This is great because I'm actually visually able to show you how this printer works. This 3D printer is a tabletop continuous filament fabrication, can allow a thermoplastic filament and a fiberglass filament to be extruded onto a single layer. Now, what they do is they have different kinds of filaments we can use: nylon with some chopped carbon fiber, and other thermoplastic filaments. We went with nylon because of the temperature requirements and everything. But with this printer, you can only, at least we haven't tried it, maybe you can, but what we can do is just get the filament that is sold by them, which is proprietary. The way we found out that it has 50% filament is I performed a gravimetric analysis on the filament piece, and we found out that 50% of it is fiberglass and 50% of it is the thermoplastic filament. So regarding ASTM standards, I don't think they are complying to any kind of ASTM, because testing and testing methods is not something they are looking into. But what they are targeting is if their 3D printer can print these materials without any clogging and things like that. So the temperatures and all that need to comply. So if you are planning to print another material with this 3D printer, you need to be able to make sure that the diameter of the filament and the temperatures to which the nozzle are going can actually extrude the filament out of that nozzle. So those are the things you want to be able to look into.
Yeah, great. Thank you. Thank you, Shreya, for this excellent answer. Our next question is, why not pultruded bars manufactured with this design?
Great question again. These are wonderful questions. I'm so excited you have such exciting questions. So, if we look at pultrusion, right, I'm very happy to share my screen to show you a pultrusion mechanism. But if we look at pultrusion, we have several. You know what? I'm going to share my screen with the for the pultrusion, because that way I can actually show. And this is from the previous presentation at ACI virtual seminar itself. So this will be great. Okay, you guys see my screen, right, Aparna?
Yeah. Mhm.
Okay, so if you look at pultrusion setup, this is a lab scale setup that we had built in University of New Mexico when I was a PhD student. Chenna Reddy is my husband now. Then he was the person who built this setup. There are several spools that are going onto a roller into a die. Now, to be able to achieve designs with multiple types of fiber orientations, we're supposed to take all these strands and get it into the die itself, which is this one that is responsible. Oh, you can't see my pointer. So the die itself, I'm bringing my pointer here. If you see the entire look of it, it's that portion where you have the strands going into, I don't know why I can't do it, but you have these strands going into a die which is covered with this foam so that the temperature is maintained. But that is the section that it comes out. The entire bar comes out as a circular section because the die has that section inside. Now think about how we can actually remodel this die or redesign this die to be able to get these orientations of fiber, and they have to maintain through that entire length of the die and come out with those orientations. So that is such a challenging process because however you get the strands, you still have to impregnate them in a resin. When you impregnate them and bring it into a die, you have to probably have another setup where each strand is being oriented in a different direction. But eventually, they all have to come together again. So it's my understanding that at this point, when I look at this, whatever we do, eventually, when it goes into the die, it still gets that same shape. So it's challenging, but I'm really open to ideas here. We can probably build a setup together, whoever asks this question. I am very excited to try this out. We've brainstormed a little bit. We just don't have the time to do this because with other funded projects it becomes very challenging. But if you are open to ideas, I'm very happy to discuss and we can see maybe something can work out.
Sure. Thank you. With moving forward with our next question, what improvements in 3D printing technology can improve this design?
Okay, that's also a great question. So, as I proposed in some of the recommendations for future work, right now with the thermogravimetric analysis, we're seeing that fiber filament itself, so the fiber, which is supposed to actually be 100% fiber, has to be melted down and therefore it has 50% thermoplastic. If that 50% fiber is increased to about 65%, OC Mateen bar about 66% fiber volume fraction, you're already seeing more fiber in there. More fiber means more stiffness, more strength. So that improvement is primary, according to me, in terms of the materials aspect. In terms of the technological aspects, I think we need 3D printing to evolve in a way such that we can intervene sometimes, but not manually. We would like to be able to intervene through the technology. If I have my G code, asking my G code to pause it for a few minutes and have a cold spray sprayed on the layer, without moisture or anything, this technology, these designs that we achieved, we could have achieved them in half the time, right? So incorporating manual techniques into the layers, that takes time. So 3D printing technology, I think, should have options of customization in a way such that if we are looking for low shear transfer or high shear transfer, or in terms of a dampener that we can add. So imagine this way, like 3-4 spools of materials, one consisting of a fiberglass filament, one consisting of a thermoplastic filament, one consists of a butadiene styrene, which is like a dampening material that probably gets printed on the layer itself to still allow bond but dampen the bond so much that the shear transfer is still maintained, but there is not too much to abruptly break the other layer. So something like this in terms of innovation, if it comes out, I'm not an electrical engineer, I would love to be all the engineers possible, but if someone has ideas to either put up a proposal or talk to other departments, we can definitely see a lot of improvements in these designs and make it actually tangible to come out as a bar in the future, because bars to be 3D printed is possible using 3D printing technology. We'll have to manage the lengths of the bars, but it's definitely possible. Circular sections with this is possible with those different fiber orientations. We're showing plates right now because that's what I did through my PhD, but the most important future work is to be able to print bars and actually show how they perform as reinforcement. So
Yeah,
lot
great.
of future aspects for this work. I can go
Yeah.
on for 3 days.
Great. That's a great answer. Thank you so much, Shreya. And with this, I think we don't have any more questions. And thank you once again for addressing all the questions we had. And thank you for the excellent presentation.
Thank
Thank
you,
you.
Aparna. Always a pleasure. Thank you.